Hi everyone, welcome back. In this particular video, we're going to start talking about di-substituted cyclohexanes and then basically expand it to multiple substitute. Like we could even talk about tri-substituted cyclohexanes at the end of this. Okay, and we're going to use 1,4-dimethyl cyclohexane as an example to start off our conversation. So that's the molecule 1,4-dimethyl cyclohexane. Notice how IUPAC number would go 1, 2, 3, and 4. So the parent chain is a ring cyclohexane, methyls at 1 and 4, so it is a 1,4-dimethyl cyclohexane. Now, even before we start discussing the conformations and the stability of the conformations, I want to bring in another level of detail here. Okay, for di-substituted cyclohexanes, we can talk about cis and trans isomerism. Okay, cis and trans isomerism. So it's like we did constitutional isomers, cis trans isomerism. This is, although not similar to that, okay, this is a kind of stereoisomerism. And we are going to see a lot of this in upcoming lectures. But stereoisomerism or stereoisomers are compounds that differ. So stereo refers to space, okay? So compounds that differ in spatial arrangement. That's the only thing different about these compounds. There's no difference in connectivity like constitutional isomers. Okay, the only thing different about them is spatial arrangement. So let's use this as an example to talk about cis and trans isomers. Okay, I'm going to draw that or two forms of that compound. One, I'm going to have a wedge for the two methyl groups, or I think I can draw where both methyl groups are on a dash, and let's compare this to, if I can compare both, all of them, let's compare this to that structure. Okay, so if you think about these three structures, they are the same, they have the same molecular formula, okay? And in fact, if you notice, the connectivity is also the same. Every atom is connected to the same other atom. There's no difference in connectivity. What's different about them is the spatial orientation. If you look at this first structure, both methyl groups are on dash bonds. Okay, that means they are pointing behind the plane of this whiteboard. Or to simplify, they're pointing in the same direction. Come to the second structure, both methyl groups are on wedge bonds. They're both pointing outside the plane of the whiteboard, or again, simply put, they're pointing in the same direction. Now, we don't mean same like they're both pointing up or both pointing down. We're saying in the same direction with respect to the plane of this whiteboard. Okay, they're pointing in the same direction. Now, another way to draw something like this, if we had to show it otherwise, would be to draw it like this, okay, where we have the ring coming out, and then maybe we say that there's CH3 over there, hydrogen here, CH3 there, hydrogen here. So both methyl groups are pointing above the ring in some sense. Okay, so over here, it's like both methyl groups are pointing on the same side of that plane of the whiteboard. So they are pointing in the same direction. So they are pointing in the same direction. So these molecules, they are called cis isomers, which means basically pointing in the same direction. notice how this other structure, one methyl group is on a wedge, the other methyl group is on a dash, okay? And so one of them is pointing outside the plane, the other one is pointing inside the plane. So with respect to the plane of the whiteboard, they are pointing in opposite directions. And this molecule is called a trans isomer. Now, I could have as well drawn a structure where the methyl at the bottom was on a wedge and the methyl at the top was on a dash, and they would still be trans. Okay, this would be the, so the two methyl groups are trans. So these two sets of molecules, when you have the methyls pointing in the same direction versus methyls pointing in opposite directions, they are called Cis Trans Isomers, okay, or more specifically Cis Trans Stereoisomers, because they do not have a difference in connectivity. The only difference is in spatial arrangement. How are things oriented, or how are groups oriented in space? In one case, we have groups oriented in the same direction. In the other case, we have groups oriented in the opposite direction. Now, I also want to point out that these two structures, where the two methyl groups are on the dash and the two methyl groups are on the wedge, they are the same structure, because if I take this molecule out and flip it over, I'm going to get that molecule, because the methyls that are pointing inside the plane of the whiteboard now, once I take it out and flip it over, they will be pointing outside. And similarly, these two structures are the same, because when I take this molecule out and flip it over, I will get that structure, okay? So these are the same, and these two are also the same. Okay, so those are cis and trans isomers. Now, in the particular case of 1,4-dimethyl cyclohexane, we will consider both cis and trans isomers when we are doing our analysis of cyclohexanes. Okay, so let's start first with the cis 1,4-dimethyl cyclohexane. And so we're talking about this molecule here. One of the cis forms, okay? In fact, they are the same. Remember that also, okay? We have the cis 1,4-dimethyl cyclohexane. Now, notice how the two methyl groups are pointing in the same direction. Okay. Now, how does this translate to a chair? Okay. So when we draw, because the cyclohexane exists as a chair. So when we draw this molecule in a chair conformation, okay, that's my cyclohexane carbons. 1, 2, 3, 4, 5, and 6. Now, I have a methyl group on carbon number 1 and another methyl group on carbon number 4. Now, when I start out to draw the conformations, I can just, the first methyl group, I can just arbitrarily put wherever I want, either on an axial position or on an equatorial position. And my preference is to always put the first group on an axial position, because it makes it easy for me to see where the other group would go. Okay, so for carbon number 1, I'm going to put a methyl group on the axial position. And then remember, there's a hydrogen here on the equatorial position. There should be hydrogens here. There should be hydrogens here, hydrogens here. We have hydrogens on that. And then we come to the carbon number 4. Okay, now for carbon number 4, the methyl group on carbon number 4 must be cis to the methyl group in on carbon number 1. And notice how they're both pointing up. So I think you could use that as a marker for where you put the second one. So if one of them is pointing up, on carbon number 4, we have two positions. One is axial, one is equatorial. Because carbon number 4 is pointing down, the axial points down, equatorial points up. And I've arbitrarily put the methyl on carbon number 1 in an axial position pointing up. So if methyl is pointing up, then the other methyl is also pointing up. So on carbon number 4, I'm going to put the methyl group in the equatorial position because that's the position that's pointing up on carbon number 4, okay? Because axial here points down. So when I've put them like that, these two methyl groups are now cis to each other, and I've drawn basically this molecule. Now, the other way to verify this is, if I pay attention to carbon number 1, the methyl group is pointing up, okay? It's in an axial position pointing up, and the hydrogen on carbon number 4 is pointing down. It's in the axial position. So one is pointing up, the other one is pointing down. That means the methyl group and the hydrogen are trans to each other. They're pointing in opposite directions. So if the methyl and this hydrogen are trans, that means the methyl and the methyl must be cis, if that helps. But simple, they're both pointing up on the respective carbon atoms. So this is the cis 1,4 dimethyl cyclohexane. Okay, that's one conformation. Now we can draw the other conformation. So for drawing the other conformation, I'm going to draw the lines, the two lines, but now slanting in the opposite direction, and then I'm going to join them. Okay, so that's what I got. That's my other chair conformation. And again, carbon 1 was the headrest. Now it must be the footrest. 2, 3, 4, 5, and 6. On carbon 1, the methyl was pointing up, okay, or it was in an axial position. Now that methyl is going to be in an equatorial position. It was axial before, now it's equatorial. Hydrogen is pointing down. Now, relatively, if you look, on carbon 1, the methyl was pointing up and the hydrogen was pointing down. And in the other conformation, the hydrogen is still pointing down and the methyl is pointing up. Okay, so that is maintained throughout. So you can go ahead and put the hydrogens on these other positions. And then when we come to carbon number 4, in carbon number 4, the methyl was pointing up. It was in an equatorial position. The hydrogen was in an axial position. So now the methyl is going to be pointing up. It's going to be in an axial position, and the hydrogen is going to be equatorial. And now for both carbons 1 and 4, if you look at it, the methyl is pointing up, the methyl is pointing up. That means they're still cis to each other. So we've drawn the same conformation, but notice how the axial methyl became an equatorial methyl and the equatorial methyl became an axial methyl now. So the conformation has flipped, or we are working with the other chair conformation essentially. Now, we have to evaluate the stability of these two conformations for this molecule, the cis 1,4 dimethyl cyclohexane. And to evaluate the stability, okay, to evaluate stability, what you're going to do is analyze the positions of the groups, okay? So if I look at the first conformation here, I have a methyl group in an axial position. The other methyl group is in an equatorial position. And what we know from monosubstituted cyclohexanes is that groups in equatorial positions, they are more stable, or they're fine because they're more roomy, they do not have any Gauss interaction. But when a group is in an axial position, it's going to have Gauss interactions, and it would have 1,3 diaxial interaction. So this methyl here, 1, 2, 1, 2, 3. So it will have some 1,3 diaxial interactions with this hydrogen, okay? The hydrogen on carbon number 3. And it would also have some 1,3 diaxial interactions with the hydrogen on carbon number 5, because that's also 1, 2, and 3 relative positioning. Okay, it's a 1, 2, 3. So there should be 1, 3 diaxial interactions. Okay, so we have some 1, 3 diaxial interactions here. So one methyl group is in an axial position, that's not good. The other methyl group is in an equatorial position, so that's good. Okay, now when we go to the other chair conformation, again, what we notice is one methyl is in an equatorial position and the other methyl group is in an axial position. So that means this methyl group is also going to have 1, 3 diaxial interactions, and it would have some Gauss interactions, which we're not trying to show here, but we know that from monosubstituted cyclohexanes. So overall, when we look at it, looks like we have one methyl group each that's in an equatorial position, one methyl group in both, which is in axial positions, has the same number of 1, 3 diaxial interactions. So what we can say is that these two have equal stability because of that, because everything is same about them. Okay, so they have equal stability between them. Okay, one of the chair conformations, one chair conformation is not more stable than the other chair conformations. In this particular case, they are of equal stability. Next, what we're going to do is we will work with the trans 1,4-dimethyl cyclohexane. Okay. Let's try to see what can be learned over there. Okay, with trans 1,4-dimethyl cyclohexane. So now we're doing trans 1,4-dimethyl cyclohexane. That's this molecule here. Again, to evaluate the stability of the two chair conformations. Okay, that is what we're trying to do here. Evaluate the stability of the two chair conformations. We're going to draw the chair conformations. Okay, so let's draw the chair conformations for this molecule here. Okay. That's one chair. We have 1, 2, 3, 4, 5, and then 6. 1, 4, and this is trans. So on 1, again, like I said, I like to put the first group in an axial position arbitrarily. That's what I prefer to do. So I'm going to put the methyl on carbon 1 in an axial position. There is a hydrogen in equatorial. On carbon 2, there are 2 hydrogens. Carbon 6 has 2 hydrogens. Carbon 3 has 2 hydrogens. Carbon 5 has 2 hydrogens. And now, on carbon 4, I have to install the methyl group on carbon 4. And carbon 4 again has 2 positions, one axial, one equatorial. Okay. On carbon 1, if you look at it, the methyl group was pointing up, okay, above the plane of the whiteboard. And here the methyl group is pointing up. Okay. On carbon 4, the methyl group is pointing behind the plane of the whiteboard, or it's pointing down in some sense. Okay. So on carbon 4, the position that's pointing down, okay, is the axial position. That means I'm going to put the methyl group over there and the hydrogen in the equatorial position. Now, overall, if you look at it, the methyl on carbon 1 is pointing up. The methyl on carbon 4 is pointing down. They are pointing in opposite directions. That means they are trans to each other. So we've drawn the trans. We've drawn a trans chair here. Okay. Now let's draw the other chair now. So if we draw the other chair conformation, okay, the headrest becomes a footrest. So you have 1, 2, 3, 4, 5, and 6. Methyl was axial. It should now be equatorial hydrogen. And then we can basically include all the hydrogens here. And on 4, methyl was axial, so that means it should be equatorial again. And those would be trans to each other. But in general, if you look, the methyl was pointing up, it is still pointing up. Methyl was pointing down, and it is still pointing down on carbon 4. Relative to, among the two groups, the methyl is still like pointing down. Okay, so those are the two chair conformations of 1,4 trans 1,4 dimethyl cyclohexane. Now we can evaluate these conformations. In fact, the second chair conformation here, if you look at it, the two methyl groups, both of them, they are in equatorial positions, which is good, okay, because there are no Gauss interactions there, and there are no 1,3 diaxial interactions. So that is good. In the first chair conformation here, this methyl is axial. That means it's going to have some 1,3 diaxial interactions there with the hydrogens that are 1,3 relative to it. This methyl is also axial, so that is also going to have some 1,3 diaxial interactions with the hydrogens that are 1,3 with respect to it. So you notice how we have 4 1,3 diaxial interactions total, or 2 sets of 1,3 diaxial interactions here, whereas we have one conformation where there are no 1,3 diaxial interactions, there are no Gauss interactions either. We're not showing the Gauss interaction here though, okay? So the red represents the 1,3 diaxial interaction, okay? So based on that, because one of these conformations has too many 1,3 diaxial interactions compared to the other one, what we can say is that this chair conformation, where both methyl groups are equatorial, is more stable, and this is less stable. Now, what does that mean? That means at equilibrium, this cyclohexane, trans 1,4 dimethyl cyclohexane, is going to spend most of its time in that conformation, very little time in this conformation, okay? So that is what this tells us which is the more favored conformation. Now, you can apply this to other examples as well. So please practice different positions, and then also try to draw these cyclohexanes in different conformations, and then try to analyze their stability. We will follow up with some solved examples. Bye.